record.
It's on the bottom.
It says it's recording.
Says recording?
Yeah, to me it is.
Okay.
Oh, yeah. It says
Okay, yeah, I've got a little record symbol here. Fantastic. Okay. So the first thing we are going to do is we are going to go to the GitHub repo for NetPyNE, github.com/neurosimlab/NetPyNE. And then we're going to go into NetPyNE proper and into tutorials. And this is where we will get the information for installation. And yeah, so we're going to run NetPyNE in a Jupyter notebook. And we're going to do that in a virtual environment. So we're going to create a virtual environment, enter it, install all our software there, and then run everything there. And this means that if you want to uninstall this, you know, it's easy, just delete the directory. And so it's a nice, clean way to do this. So hopefully this single command will work. This will be the simplest way to do this, is copy this big, long command and open a terminal, right-click. New window. I'll make the text a little bigger. And yeah, so I do most of my work on the desktop, and I'm gonna just work in a temp directory. So I've got this temp make alias, which I use temp directories all the time. So I can use temp make to say remove an existing one, make one, and change into it. So now I'm in a temp directory, and I'm going to copy this big long command and paste it into my terminal. Actually, before I do that, we're going to open a Finder. So I'm going to click on my desktop and hit, I'm running on a Mac, so hopefully somebody's running on Linux, and hopefully you're all following along. I'm going to open a new terminal, Command N, and I'm going to look at my desktop, and I'm going to be in my temp directory, and right now there's nothing in there. But I'm going to install this. I hit enter in my terminal, and it creates this NetPyNE toots directory, and then it starts creating this virtual environment that we'll call env, and it's going to install all the software.
Wait. Sorry, I'm a little lost. Sorry, just going back to the first page, the NetPyNE page. What do I go under? Examples.
So we are in. So if we start from the NetPyNE main page, then we go into the NetPyNE directory there, and then way at the bottom of that we go down into tutorials.
Oh, okay, got it.
And then it should bring up, whenever you have a README in GitHub, it nicely displays it.
Yeah, got it.
So this
perfect.
is
Okay, thank you.
Instructions, yep. And so yeah, you're just going to copy this big long command and open your terminal and enter it. And then your browser should pop this up. It should start running Jupyter. Okay. But let's take a quick look at what happened. So in our NetPyNE toots directory now, we've got the env. And this is our virtual environment. So this contains everything we've just installed. And to uninstall, all we have to do is just delete this whole directory. So it's nice and clean. And so yeah, this has all the stuff that we're going to need to run. So it has IPython, it has Jupyter. Everything is installed in this local virtual environment. So even the Neuron stuff is here. And so yeah, then went and cloned NetPyNE from its GitHub repository. And then that tutorials directory, it just copied it up into this level. And then it started running a Jupyter notebook, which we can see in my browser here. So is everybody running this? And if so, have you gotten to the browser being open like this?
I have.
Not yet.
Yeah, mine's finished installing.
Mine's slow.
Yeah, no, it may take some time because we have to install everything. So NetPyNE has a ton of dependencies. So does Neuron. It's got a ton of dependencies. And so the first time you do this, it's going to have to install all those into your virtual environment. Yeah. But after the first time, you can just enter that virtual environment that already exists. So in the future, it'll be much quicker.
Yeah. Can you show the path to the tutorial once more? Somehow I'm not able to find tutorials inside the NetPyNE.
Yeah, so if we go to Neurosim Lab,
yeah,
then we go into NetPyNE.
Right.
Then we go into NetPyNE again. So this is kind of
Correct.
maybe
Yeah.
the tricky spot. And then the bottom there is tutorials.
I don't see tutorials here. I have everything else, but not tutorials.
Try refreshing. Are you sure you've got the path right? You
Um,
want to be in development.
okay, I think,
Let me share this link.
yeah, please. Thank you.
Well, I just did it in general, but I'll also try to find the chat here, which I don't know how to find. Or chat, there we go. And okay, so I can paste. Yeah, I pasted the link into
Okay, thank
the
you.
chat as well, and that will get you right to
Okay,
NetPyNE.
yeah.
And then once you're in there, you click NetPyNE again, and then go down to tutorials. And I guess I can, yeah, why don't I just share that whole link instead of making you click around? Okay. So yeah, once you're here, then you want to, double click or triple click in this, in the commands here, copy that, go to your terminal and paste that in, and then hit enter. And that'll create this virtual environment that we're calling env. It'll install NetPyNE and all the necessary software, and then it'll move the tutorials directory up to here just for easy access.
Hey, Joe, is Neuron in there? I was poking around. I didn't see where.
It is. Neuron is in, but Neuron, we don't clone the repository. We just use the pip install for Neuron. So it ends up in bin here. You can see we've got Neuron GUI and Neuron IV and Neuron IV MODL. So that pip install NetPyNE installs it. It just doesn't clone the repository before it does that.
So it's all in bin there. Okay.
Yep. And yeah, while people are still, and let me know when everybody's ready, I'm going to open a new tab in my terminal. So Command T gets me to a new tab. And I'm in my temp directory, and there's my NetPyNE toots, so I can change into that. And yeah. So this installs and creates a virtual environment that you don't have to use through Jupyter. So once you are in your NetPyNE toots directory, pwd, I'm in my NetPyNE toots, ls, I can see I've got my environment there. I can activate my virtual environment in the terminal and just run things here. I don't have to do it through Jupyter. Okay, so if I want to activate my virtual environment here, I'll do source env bin activate, and I'll hit tab with AC, and that finds activate. So if I source this file in my virtual environment, now you can see on the left of my terminal here, I'm in env, I'm in this virtual environment. And any changes I make here will only affect it here, and so on. So I can now run, this tutorial directly from the command line, but we will do it in Jupyter right now. So is everybody ready with a web browser open to our Jupyter?
No, so I'm running this on Linux, and Jupyter has trouble opening the a file, some file. Access pops up a browser window. Access to the file was denied. Fileless. Home/Craig.
Would you do me a favor, Craig, and would you copy that output and make an issue on GitHub?
Yeah, sure.
So I can then try to figure out how to fix that on Linux. Yeah, I'm running Mac OS Catalina, and so hopefully it'll work on Mac, and with a few tweaks, it should work on Linux as well.
Okie doke. And is just so I can try and keep following along. Source deactivate env. That'd be how to come out of the virtual.
So deactivate is much easier. You're already in your environment, so there is a simple alias, I guess. Deactivate. Now I'm out of my environment. See how it disappeared? The prompt there. To get back in, I source env bin activate, and I'm in. Deactivate, and I'm out. So yeah, so let's look real quick here. Let's look at which Python 3. I'm outside of my virtual environment, and my Python 3 is in user bin Python 3. Now let's activate our virtual environment, and let's do which Python 3. And now we can see the Python 3 I'm using now is in my virtual environment. So once you're in your virtual environment, it just affects it locally, and you can just delete that. No worries about uninstalling or any of that. So yeah, so let's go to our Jupyter web browser, and we can see we are in this NetPyNE Toots directory. We've got, no, we were in tutorials, excuse me, tutorials. So we've got these files here. We've got NetPyNE Toot 1 with this notebook. So yeah, in our web browser, we'll click on the NetPyNE Toot 1 directory, and then we'll click on the NetPyNE Toot 1 Jupyter notebook. So yeah, I'm just going to pause for a second here and make sure everybody is at this point with me. So if you would let me know if you're not.
Sorry, what is the command to switch between the env? Because I could deactivate it, but I cannot find the command to get back in.
To activate it, it's going to be, you want to run the source command, which basically runs a file, and then you want to source the env, and in the bin, it's the activate. And so you want source env bin activate. I'll copy this command into our chat. So that's how you get into your virtual environment. And to get out, it's just deactivate. And then, yeah, once you're in your virtual environment, you can open a brand new Jupyter notebook. So I'm just going to type Jupyter notebook, and that should open a brand new one. Oh, but it did it in my other browser. Okay, let me make this browser active. Command W to close the tab, Command T to open a new one. I am in my temp. I want to cd to NetPyNE Toots. And I want to activate my virtual environments. And then I want to Jupyter notebook. There we go. So yeah, it's opening a new Jupyter notebook here. And what we did by creating this virtual environment is we added a kernel to Jupyter. Jupyter can't run on virtual environments. Jupyter has to create a kernel, which it then uses. But so yeah, normally if you open Jupyter, the only kernel available you can choose from will be Python 3. But the way we installed it, we've also got this env, our virtual environment with all the things we've installed, available to create a new Jupyter notebook in here. So, you know, there's nothing there yet. It's just empty. But you can, and it created, if you'll notice, oh, here it is, the Untitled.ipynb. So you can save it to your local computer and stuff as well. So these Jupyter notebooks are actually really cool. But we are in NetPyNE Toot 1. And yeah, we want to run, okay. So here we are in NetPyNE Toot 1. Everybody go back to here. And this whole preliminaries tab just explains the installation. And so you can go through that on your own if you'd like, but for now we'll just skip it since it's already there. In my NetPyNE, or in my Jupyter notebook now, it just consists of a series of cells. So this first one is a big long cell that's just text. And then this is a cell that's just text. This is a cell with text. This is a cell that actually runs Python code. Okay, so it's just a series of cells in a Jupyter notebook. And if we want to add a new cell, we can click this plus button, and we've got a brand new cell that we can do stuff in. We can get rid of that with the scissors button. Yeah, so there are basically three types of cell in a Jupyter notebook that you're going to be using. Markdown is just for text, but it allows you to format it a little bit so you can have headlines and things like this. The other possibilities are a raw cell, so it just whatever text you put in, it will show that raw. And the other one is a code cell, like this one down here, where you can see it's actually like an IPython prompt here. And if we run this, it'll run it in our kernel in our virtual environment. Okay, so just a quick intro to Jupyter notebooks. And the way you execute a cell in a Jupyter notebook is you have to hold down Shift and then hit Enter. So we're in our first cell. I'm just going to hold down Shift and hit Enter, and it's going to bring me past all that installation stuff into the next cell, which is the introduction to tutorial 1. So we're just going to create a simple network model, relatively simple. It's actually quite complex. But 40 parameter-like cells with 2 compartments connected with a 10% probability and an excitatory synapse. So nothing too fancy. And at any time, if somebody is behind or needs me to wait or has any questions, please let me know. Speak up. Okay.
Is something supposed to happen when you hit Shift Enter?
Not on these text cells because it's just text. So I just hit Shift Enter.
How about the command cells?
So now we're going to start the tutorial. I'm in the text cell before our first code cell, and we want to instantiate our network parameters. So as most of you know, in NetPyNE you need netparams and you need symconfig in order to set up your simulation to run. So I'm going to hit Shift Enter in this text cell, and now I'm on a code cell. So this is actually going to run in Python. So I'm going to import specs and sim from NetPyNE, and I'm going to set up these objects to hold the information for our simulation. So I'm going to hold down Shift and hit Enter. And when it's running, you can see a little asterisk in the line here. And once it's done, it'll give you the in1, like IPython normally does. So this is taking a moment to do for me, but now we're done. So it's done, and we've got these things imported. So let's add a new cell real quick here, and let's just see what's going on. So I hit the plus, and the default is a code cell. So whos is a command in IPython you use to see what are all the variables in my workspace. So I'm going to type whos, and I'm going to hit Shift Enter, and
Oh,
yeah.
cool.
And you can see that now because I've imported NetPyNE, or I've imported specs and sim, they show up, and I've created the objects to hold our simulation. I've created netparams and symconfig. Okay. And both of these come with a lot of defaults set. Obviously, to run a simulation, you have to have a lot of settings, but most of those will be in the defaults, and we'll only be changing a few. But yeah, but right now, for example, you could use tab completion to look at what's in these things. So instead of whos, let me type netparams dot, then I'm going to hit tab. And here's all the things that you can do in netparams. You can add cell params, add stim source. You know, you can. There's all these things that come with this object sort of set as defaults. And
So what's the advantage of running in Jupyter versus just IPython?
This makes it very easy to save whatever you do at the end. So literally when I developed this, I started a Jupyter notebook and I started doing this. I typed in the introduction, I typed in this code, I ran it, and then I did all the other steps, and then I saved it at the end as this Jupyter notebook, which can now be used to go through tutorials. So you could even use it as like an electronic lab notebook, which I might start doing on projects. Yeah, so right now we can save this. We can click save, and that'll save this to our NetPyNE toot1.ipyneb. Let's do a file save as, and then any changes we make right now will be in a new file, and it won't affect the original one. So we'll make a new file called whatever you want to call it. I'm going to call it NetPyNE toot1_active, whatever. I'm going to save that. And now I can see in my Finder that I've got this NetPyNE toot1 active Jupyter notebook. So all these changes that I make will be saved into here, and I can share them with other people or whatever. Great. So we've created netparams and symconfigs. The next thing we need to do is create a cell model. And so we do that.
How do you show and hide the menus at the top? I can't see them, so I figure I'm hiding them.
Or what?
Yeah, those. How do you show that?
Bill, I had that same issue on Linux as well. I don't know if that might be a bug for Jupyter.
Oh, you don't see the commands on top?
No.
Often no.
I had this problem in the past in Japan in the tutorials, and so yeah, Google it, and Stack Overflow somewhere has a solution where there's a command you can enter that hides or shows that. So I'll bet that's what it is. But we'll look into that later. Yeah, so you don't need the commands on top necessarily because you can just hit Shift Enter to activate any cell. So again, this hasn't been run yet because it's blank here. So I'm going to hit Shift Enter, And now it's the third command I've run. So this is done. So yeah, let's add a new cell right here. And I'm going to type net params dot cell params and hit shift enter. Ah, look at that. We've got this pyramidal PYR cell type in our cell params. And right now it just has an empty sections dictionary. Okay. So first, let's specify the SOMA compartment properties. So we will shift enter in this cell to add a SOMA dictionary to the pyramidal cell sections dictionary. And then we'll just put in some parameters. It has to have a diameter, it has to have a length, it has to have an axial resistance, and it has to have a membrane capacitance. So we'll shift enter on that to enter those values. And then we'll add a mechanism. Right now, it doesn't do anything because it doesn't have anything in it. So we're going to add an HH mechanism, Hodgkin-Huxley mechanism, to it. And this is a default. It's built into Neuron. So we don't have to compile a mod file or anything. This mod file exists in Neuron and is precompiled. And there are some settings we can play with in this Hodgkin-Huxley mod file. And I'm going to have to remember to hit Shift-Enter in there to put that into our Python, into our terminal. And again, so the HH mechanism is built into Neuron, but it is based on a mod file, and you can see that mod file here at this link to see what's going on. And yeah, let's just click on that link real quick. This is what the HH mod file looks like. And yeah, we can see the suffix is HH, so that's how you call it. And it's got a bunch of parameters in this mod file. And so we can change these, but we have to know their names. So we'll have to go into this mod file, see what these names are. And then we can go back here, you see, and those are just the defaults that came with it. But now in the future, we can change any one of those we want to see the effects. Oops, I clicked it again. Okay, so we've specified the SOMA. Now we want to create a dendrite to attach to that SOMA. And we're going to add this in a slightly different way. So when we added the SOMA, we added it directly to the cell dictionary. This time we're going to create a dictionary that holds the entire dendrite, and we'll add it to the cell parameter dictionary at the end. Okay, so we'll just make an empty dictionary called dend. We'll add the same geometry stuff that we added to SOMA. This is going to be a little bit different. It's going to be a lot skinnier and a lot longer. We'll do that. And in our dendrite, we're not going to have the full Hodgkin-Huxley mechanism. That includes a passive current. The Hodgkin-Huxley includes a sodium. Really loud. Everybody mute.
What is that?
Bill, you're muted.
Oh, there we go. Now it's fine again. So yeah, so in the dendrite, we have to specify its geometry, and then we'll just add a very simple passive mechanism. It won't have the active Hodgkin-Huxley stuff in the dendrite. But again, the pause mechanism is a mod file in Neuron, and you can see what it is here. Because we want to connect the dendrite to the SOMA, we have to add one more thing to this dictionary. It has to, the topol. We have to add the topology to this dictionary to say, what is its parent? Where on the parent does it attach? Where on itself does it attach? So it attaches at the very end of the SOMA and at the very beginning of itself. And shift enter to do that. And then, yeah, so that's just a dictionary floating around in space. We have to actually add it to our cell params dictionary to then get it into NetPyNE. And so we'll shift enter on that to do that. So now we've specified a 2-compartment cell model, and we're ready to move on to making a population out of this cell model. So shift enter to create a population of cells. And in NetPyNE, you can connect individual cells, but in general, you're going to connect populations. And so we want to create a population of cells, and these are sort of pyramidal-like excitatory cells. So we're just going to call them PYR, although you could, the cell type is called PYR. We defined that earlier. We're going to call our population just E for excitatory, and we want 40 of them. So yeah, so adding this E pop params dictionary to our NetParams defines our population. In order to connect cells, we're going to have a synaptic model, and we're going to create one we'll call EXC for excitatory. by adding a dictionary to the synaptic mechanisms parameters dictionary in NetPyNE. And again, we're going to use a standard neuron mod exp2syn, and you can actually see that mod file with the link here. But yeah, it's a very basic double exponential, so an exponential rise and exponential decay on this synapse. And you can set the time constants and the reversal potential and stuff. So we've got that synapse. Now we have to use it to actually connect our cells. And so we have to add a rule to the conparams dictionary in NetPyNE. And we could name this anything, but it's good to have descriptive names. So we'll just call this E to E, because it's from our excitatory population, or from our E population to our E population. This is a good name. To define connectivity, you define pre-conditions and post-conditions. So where is this connectivity coming from, and where is it going to? It's going from our population E to our population E, so both pre and post are the same. Any connection is going to have a weight, and that's going to depend on the mod file, the synapse model you're using and stuff. But for this mod file, the weight of 0.005 gives good results. There are a variety of ways to define the connectivity between populations. The simplest is just to do it with probability. So we'll set a probability of 0.1. We'll create a 10% probability that any one E cell connects to another E cell. We want to have a synaptic delay. So once one E cell spikes, it takes time for that to travel down an axon and then hit the synapse and then affect the next cell. Neuron just does that by a delay. So we're going to have a 5 millisecond delay. If this neuron activates 5 milliseconds later, any neuron it's connected to will see that excitatory postsynaptic potential. You have to say which synmech we're using. We've only defined one, so that's what we'll use. And you have to say where that synaptic input is going to arrive on the postsynaptic cells. So most synapses arrive on dendrites, so let's have it arrive on our dend section. And let's have it arrive at the very end of our dend section. 0 is the beginning, 1 is the end. No matter how long or short it is, it's defined by 0 and 1. And we'll put it at the very end of our dendrite section. So we'll hit Shift-Enter there, and that'll put those all in place. So great, so we've got our network parameters all set up. Now we have to deal with our other object that's necessary, and that's the simulation configuration. And again, this is just filled with defaults, and we're just going to change a few for our purposes. We're going to give it a file name, so it saves it under this name. I call it NetPyNE 2.1, but you can call it whatever you want. We're going to reduce the simulation time a little bit. I think the default is 1,000 milliseconds or 1 second. We're going to bump that down to 200 milliseconds. And our DT, or the time step for the solving of all the equations involved, this is fairly simple, so we're going to make it a little larger just so the simulations run more quickly. And again, any questions, anytime, please raise your voice. I'm going to Shift-Enter that. And we're going to set up a few more things in our configuration before we do this. NetPyNE is not going to record everything. There's a million things we could record. So you have to explicitly set the things you want to record and the cells you want to record from. So for this model, we're just going to record from one cell. We're going to record from our very first cell, which has the GID, or the global identifier, of 0. So we'll record from one cell. And the traces we will record in that cell, let's just record the voltages right now in the soma and in the dendrite. And so, yeah, you can call a recorded trace whatever you want, but then you have to say where you're recording and what you're recording. So we are recording in the section soma, we're recording in the middle of that soma, and we were recording with the neuron variable V, the voltage there. And the same thing in the dendrite, but we'll record at the very end of the dendrite where our synapses come in and stuff. So I'm going to hit Shift-Enter on that, and now it's been added to our sim config dictionary. And then quickly, we'll just add some plots that'll automatically run every time we run this so that we see that it did something. So we will plot traces. And by default, this will just plot every trace we have, every trace that got recorded. And because we're recording cell 0, we don't actually have to say include cell 0. But this is a nice feature. You don't have to set every cell you want to record from there. if we added, for example, if we said cell 0 and cell 1 here, cell 1 would be automatically added to the things to record from. And so there's a couple ways to get it in there, but we'll just record from cell 0. We want to save the fig, so we'll set these options to true. We'll also plot a raster, and we'll save that. So I shift entered on that. And yeah, one thing we have to do before we run this, in order to see these figures in a Jupyter notebook with using matplotlib, you have to enter this command. So %sign matplotlib inline, and now the plots will show up right in our Jupyter notebook. Great, so we've created this nice model. Now we want to run it and see what it does. So it's a simple command, create, simulate, analyze, and we feed our objects into that. I'm going to hit shift enter in there, and we will see the output. So it started, it created a network of 1 population on 1 host, 40 cells, made a bunch of connections, 161 connections. It ran the simulation for 200 milliseconds, gathered all the data, analyzed, and made those figures, and plots the recorded cell traces. So you can remember we recorded vSOMA and vDend from cell 0, and that shows up here. And it's pretty boring at this point. It just sort of settles into its resting membrane potential. We set it to plot the raster, but there were no spikes available, so it did not plot the raster, and it completed successfully. So I hope everybody else got this to run and complete successfully. And I think no news is good news, so I'll carry on until somebody stops me. Great. Okay, so yeah, from that text output and from the figure, we can see there was no spiking in the network. But now if we look at our directory here, oh yeah, there it is. So in our directory now we have this traces figure that was automatically generated by NetPyNE when we ran this, and it was saved in our directory. No raster was produced because there were no spikes. Okay, so now let's so now let's do I'm going to add a cell here and just do a quick whos, shift enter, and we can see we've got this this sim now, and that is the simulation we just ran, and we can find all the stuff in there, and we can run figures from in there. So for example, if we want to plot these traces a little bit differently, we can type sim.an, and then I'll hit tab, and it'll pop up analysis, and I'll hit dot, and I'll hit PL, and I'll hit tab, and it'll bring up all these possible plots. So we can plot, for example, let's plot these traces, but let's overlay them so it's a little more interesting. Overlay equals true, shift enter. And yeah, so it plotted the traces again, but now they're both on the same plot. And so yeah, there are a variety of options on every NetPyNE function.
Wait, how do you get the menu to pop up again after analysis?
So this is called tab completion. So if you type sim.an and hit tab, it'll pop up analysis or analyze. Analysis is what I want.
Okay.
I'll hit again, and I'll hit tab, and there's a whole bunch of stuff. But if I type PL and then hit tab, then it's just stuff that starts with PL.
Okay. So, all right, got it.
And yeah, and so we've got a great website for NetPyNE that has all the information about all these functions. But if you're in here and you want to see, hey, what are all the options available, you can do sim.analysis.plottraces ? And then hit shift enter, and it'll come up. It's a doc string, so it's the information about all this code. So we can see you can include different things. You can set a time range. There's a lot of different options available to this plot. Great. So yeah, so we plotted our traces and overlaid them, and we see this. Even though it's not doing anything, we can plot the 2D connectivity of the network. And here's a link to the website where you can see that, that code, but we'll just execute it, plot 2D net. And here's our 40 neurons, and each one has a 10% probability of connecting to any other one. And the defaults set up a space in space And you know, the neurons were randomly arranged in that space, and you can change these defaults. You can change the size, the number of neurons, you know, all that stuff. But the defaults are there, so you can just quickly and easily do this. We can also plot the connectivity matrix, which will be a little bit boring at this point. So it's by default, it plots the connectivity between populations. Well, we've only got one pre-population and one post-population, so it's a little bit boring, but the connectivity is about, you know, 0.08, its strength. One of the options in this plot con is to plot the connectivity by cell instead of by population. We have to change the feature to weight, because between any two cells, there's only a weight. Between populations, you can have a strength, which is sort of an average weight. But between any two cells, you have to switch it to the weight feature, and then we group by cell. Shift enter on that, and now we can see 40 cells on the pre, 40 cells on the post, and the weight of those connections is all the same. We could randomize it a bit more, but yeah, you can see in this plot which cells are connected to which other cells. And again, our simulation didn't do much. It was pretty boring. So let's add a stimulation. We're going to add a current clamp. And you do this by adding a dictionary entry to the NetPyNE stim source params dictionary. And we'll just call ours iClamp1. It'll be our first iClamp. And it's a built-in neuron type called iClamp. The current, it'll last for 5 milliseconds. It won't start until 20 milliseconds into our simulation, and it'll have an amplitude of 0.1 nanoamps. So let's specify that by hitting Shift Enter. And now we have to specify a target for that stimulation. So we have to add a dictionary to our stim target params dictionary. And again, descriptive names, we can name this whatever we want, but we're going to connect this iClamp1 to cell 0. So let's call it that. We have to specify the source is what we just defined. And the conditions, you know, you could do a lot of different things under conditions. You could do a pop, you could do a population, you could do a cell type, you do a cell list, you could do a lot of things. We're just going to put it into one cell in a cell list. So it's just going to go into that cell 0. And we're going to put it, that stimulation into the dendrite at the very tip of the dendrite. So let's Shift Enter in this, and that adds it. So now, so now we want to create, simulate, and analyze that model again. So we'll go in here and we'll, oh, I got bumped up. Give me a sec to go back down. Here we are. And that's been entered because it's got 29. This one has not, it's empty. So I'm going to go in here and I'm going to Shift Enter. And that ran very quickly and gave me the number. And now we can see, I'm sure there was spiking this time. Yes, now there were 243 spikes. So now it's a lot more interesting. We can see the voltage in our dendrite, the voltage in our soma of cell 0, and we can see a raster plot of all the cells and they're spiking over time. So the x-axis is the time of our simulation, and the y-axis is just the cells, cell 0, cell 1, cell 2, cell 3, and each little blip is when a spike happened. These are kind of hard to see. Let's improve our plots a little bit. So let's overlay our two voltages. And now it's a little easier to see what's going on. We've got our dendrite and our soma voltages. And this is in cell 0 where we fed that stimulation in. So you can see that the dendrite actually activates first here, because that's where the stimulation entered, was in the dendrite. And that eventually causes this action potential in the soma, which spreads to other cells, which spreads to other cells, which then kicks this network into gear. The raster plot, let's make our marker a circle and let's make it larger just so we can see a little better what's going on. Okay, now it's easier to see the spikes in time. And we can see our cell 0 was the first to spike. We delayed it by 20 seconds, our current clamp. And then we said, oh, then it takes 5 milliseconds for anything to happen. So we start seeing it about here. And then 5 milliseconds later, every cell that this is connected to is going to get an excitatory postsynaptic potential, and it'll spike, and then it kicks through the network, and we start to see some interesting network activity. And again, you can see all the options in these plots on our website, on the website. The connectivity matrix is going to be a little more, I don't know why it keeps pushing me up. Where to go here? Yeah, so the connectivity matrix, because I haven't been hitting Shift Enter, so it brings me back to the last time I hit Shift Enter. The connectivity matrix will be a little more interesting now because we've got both a population and a stimulation. Still not all that interesting. So now, once you've got a model going, typically you're going to want to record a variety of things and see what they're like. So the first thing we'll do is we'll get rid of the voltages we were recording. So we'll just enter, get a blank dictionary into record traces. And let's turn off that plot raster because we're not going to use that for a while, and that way it won't pop up every time. But let's record and plot the conductances in the SOMA. So we've got that HH mechanism, the Hodgkin-Huxley mechanism. And if we look at its, and this link goes there, but if we look at its mod file, we can see that the conductances are called GNA, GK, and GL, and we can record these conductances. So we want to add these traces we want to record to our record traces dictionary. So we'll call the somatic conductance GNA, and we want to record it in the SOMA, in the middle of the SOMA. We want to record it from that HH mech, and the variable internal to the HH mech is GNA. That's what we want to record. And we'll do that for sodium, for potassium, and for the leakage. So Shift Enter will set up those conductances. And then we can rerun that simulation. So I'll Shift Enter in there. And now we can see we're not recording voltages anymore. Now we're recording conductances. We've got our GK, our potassium, our leakage, and our sodium conductances recorded in the SOMA. So at this point, let's make this a little more interesting. It's kind of hard to see what's going on there. So let's overlay these plots and let's zoom in on one of those spikes. So I'm going to Shift Enter in here. And now we can see our plot is from 90 to 110 milliseconds. And it overlaid the potassium, the leakage, and the sodium conductances. So now we see the standard Hodgkin-Huxley action potential. Sodium activates, which drives the cell to spike. Potassium activates to bring it back down to resting membrane potential. And then the leakage current sort of gets everything back into balance. Cool. So we've recorded our conductances. Let's record from one of our synapses. As we discussed earlier, they're set to use exp2syn, which is the built-in neuron mod file available here. And if we look in that file, we can see that its current variable is just called lowercase I. So we'll set up, we'll clear our traces again. So this is all we are recording. And we'll just call this trace isyn0. We'll record, we put all our synapses into the dendrite at the very end. And we want to record from that excitatory synmech that we defined. And the variable we want to record is this I. And we'll also record the voltage in the dendrite just so we can see the interplay. So we'll Shift Enter in there and Shift Enter again to simulate it. And we can see we've got the dendritic voltage plotted and the synaptic current plotted. So you can see where the synaptic current comes in. Every time it comes in, there's an excitatory postsynaptic action potential here. But obviously there are multiple synapses coming into the cell. Let's record from all of them and see what's going on sort of on a more network level. And so, yeah, so there are multiple synapses here. Let's plot all of them. But first, we really need to know what they are. And again, I'm going to insert a new cell here with the plus. And everything in our network is defined in sim. So we can hit sim.net.tab, and we can see what is all available here. And we want to see the connections that are there. So we want to see, excuse me, no, we want to see all the connections in cell 0. So in sim.net, we got all cells and all pops. In sim.net, all cells 0 is the one we're recording from. And it's a dictionary, so we can see the keys there. Shift Enter. So in this all cells in our sim, we can see that we've got a GID, which will be 0 for this cell. its cons, its stems, its sections, and so on. So we can, yeah, so we just saw that. So we can look at sim.net.allcells0 and in the cons there. And now we can see that in the cons, here we go. In the cons, there are 1, 2, 3, 4, 5, 6 synapses that get formed on this cell 0 that we're looking at. And they come from a variety of cells or whatever, you know, and here's all the information for those connections. So we want to record now from all those synapses, all the current from all those synapses that are coming into this cell. And we could hard code this, right? So I could say that trace 6 is this and trace 10 is this. But let's do it a bit more Pythonically, a bit more programmatically, because you know the number of synapses could change on different simulations and stuff. So let's try to find all those synapses and record from them programmatically. We'll set our record. We'll empty our record traces dictionary. Let's also record from the soma to see what's going on. We'll record from the soma and the dendrite. And again, this is where we could just go through those connections one by one and do it the same way we did for soma and dendrite. Say record this, record this, record this. But let's loop through this instead. It's a little more fun. And somebody's talking to me on Slack. Is anything important going on or?
No, Joe, just me. Don't worry.
Oh, okay, cool. Great. So we are going to create a for loop to just loop through these cons and then set up the recording for them. And in a for loop in Python, you can do this cool thing called enumerate, which gives you an index in your loop. So if we just did for something in sim.net.allcells, it would just have that thing. But this way we can have an index with this enumerate. And so, yeah, we'll create a trace name. We'll call it isyn underscore the cell it's from. So we'll get that pre-GID to call it. And yeah, so we have to create a dictionary to hold this. We'll just have it be none at first. This will create the key to hold the dictionary. And then we will record traces, that trace name that we just made in the dendrite, location 1, x, the variable I. But because there's multiple synapses there, there'll be an index. And so we specify which one. So each loop, this will say index 0, connection 0, and it'll do it. And it'll say index 1, connection 1, and it'll loop through all this into our simconfig.record traces. So right now we can print that and see what it looks like. And it's not terribly easy to see, but you can see we've got our vsoma and our vdend that we manually specified. And now I've got isyn6, the current from synapse 6. I've got isyn10, the current from synapse 10. So now at this point, we can run this simulation. And we can see we're recording our dendrite and our soma, and then a bunch of synaptic currents. And at this point, we can't really, NetPyNE plotting is really meant to be pretty basic. Run a simulation, see some basic plots. But we're going to want to manipulate data and make our own plots and stuff. So we'll do that now. We'll extract this data we've recorded, and we'll make our own nice plot. So what we're going to do is going to make a plot with two figures. The top one will be the somatic and dendritic voltages. And the bottom one will be all those synaptic currents. So we should be able to see the two line up nicely. But first we'll have to extract all that data. And again, once you've run a simulation, everything lives in sim. And our data lives in all sim data in a collection of dictionaries. So we can see there's SPKT, which is an array of the spike times in the network. Spike ID, which is the IDs of those, the cells those spike times come from, an array of those. And we've got our traces, vsoma, vdend, and all our current traces. So let's look at what does vsoma look like? Is it an array or is it, oh no, okay. If we look in vsoma, that dictionary, we see it's another dictionary that has cell 0 as a key. If we'd recorded a bunch of cells, this would be a list of all the different cells we've recorded from, but we only recorded from cell 0. So at this point, we can extract our data. In the all sim data dictionary, t is our time variable. So we want to extract that into a variable we'll call time. And we'll extract our vsoma and vdend from this dictionary. And then we'll do a for loop to get all those synaptic currents. For each syn plot in the syn plots, we will specify, we'll extract that data. And so now at this point, we can make a custom plot with all that data we just extracted. So we'll import matplotlib, create a figure, and on the top, we'll plot soma voltage versus time and dendrite voltage versus time. And then on the bottom, we will plot those synaptic currents versus time, and we'll create labels and a legend and stuff. And we'll even save it to our directory here. So yeah, let's shift enter in this cell. Ah, cool, we've got our custom figure here. And it should have showed up here. Yes, so it saved it in our directory. And yeah, so we can see this is cell 0, the dendritic and somatic voltages. And these are all the synaptic currents entering cell 0. So every time you see an EPSP here, that's because a synapse entered there. You know, except when the soma can also drag the dendritic voltage up. So there's no corresponding synaptic activation here. That little pulse happens because the somatic voltage is dragging up the dendritic voltage. And yeah, so that's just a matplotlib plot. So you can, you know, clean it up a lot, make the font size better, do a bunch of different stuff. And yeah, at this point, we can reset everything and then run this whole thing in one single Python file. But no sense doing that because we've just gone through it all. And again, so this is just going to live in, you know, I created a temporary directory on my desktop, ran that install, and it makes NetPyNE toots. The tutorials live here. That NetPyNE tutorial 1 we just ran is here, and it's got you know, the traces we saved and our custom plot we generated. So yeah, I think this is a pretty good overall introduction to NetPyNE, and most simple things people want to do, I think, should be covered by this. But at this point, I'd like questions, and if anybody has suggestions for other things that should be included in this sort of lowest level tutorial, this would be a great time to hear all those. So let's open the floor up.
Very nice, Joe. Is multiple parallel processing included on this, or
it will be?
It's not currently on the, okay.
No, there's, I mean, this is real fussy. This is a ton of work to get this. It's cool. But, so yeah, now I have to figure out how to, because you have to install MPI on your own machine, and then you have to sort of link to that in your virtual environment. And I'm working on that now, and hopefully that'll be done soon.
Okay, no, this is very nice. Thank you.
Yeah, no, thank you guys for your attention. So everybody get it to run? Did anybody have any crashes or questions or suggestions or anything at this point?
You ran pretty smoothly. That's a phenomenal job. Thank you.
Cool. All right, fantastic. So since there's no news, I'm assuming it's good news, and it went smoothly for everyone. And yeah, this should be a nice. Now, hey, how do I record Volta? You know, you can look at this tutorial and copy out some code, and you're ready to do some cool things.
Yeah, I have a question. So,
yeah, please.
Is it like feasible to use this kind of like as a debugging interface? Because I see like we have this like nested installation that everything we do there is like separated from our local installation on Python. So we can just like use that for that purpose as well, right? All right, thank you.
Yeah, so I would use, if I were you, so I was working with the Cardiac group a few days ago, and we're trying to get them up to speed using NetPyNE and Neuron and Jupyter notebooks. And then we were trying to get up into batches, but we didn't quite get there yet. But while we were working, we built up a Jupyter notebook. So Suri was typing away, let's talk about Git commands. So she made a text cell with all the useful Git commands. And then we ran some stuff. So you make a code cell, and then you can run the code. And then you save this to GitHub, and anybody can run this. Oh, yeah, one thing to know is that before you commit your Jupyter notebook to GitHub, you want to clear it first, right now it's got a ton of data and a ton of figures in it, which you do not want to put on the GitHub repo. So to do that, you would go to kernel in the menu, and I'm sorry, you guys don't have the menu on top, but you click on kernel, go to restart and clear output, and then click restart and clear all outputs. And then click the little save button, and that'll save it to your computer in the file. And now this is totally empty. It's a very, very small file. So the tutorial itself is very small. When you filled it in, it's going to be huge. You don't want to push that to a repository. You just want to push it empty.
Mhm.
Can I ask a stupid question? So then to get back into the Jupyter notebook, that's done through the terminal, like we did at the beginning.
Yeah, exactly. So so in the future, you've already created this environment. We've installed all that software. We
Right.
don't have to do all that time-consuming stuff anymore. We can just change to, I'm in my temp, I'm in NetPyNE Toots. And my
So you,
environment is there.
okay.
So I can just change
Okay.
here, and I can source and bin activate. And now I'm in my environment. I don't even have to run Jupyter Notebook. I can run, there's not right now, this tutorial will be in a Python file also, and you could just run that Python file of this tutorial here without even going into Jupyter. But if you do
So
want
if
to
I-
go to Jupyter,
yeah.
you can type Jupyter Notebook, and it'll open. a
Oh,
new
and then
one.
it'll open it. Okay, got it.
Okay.
Thank you.
Yeah.
Okay.
All right. Wow, that was really fun, and I'm really excited about these tutorials. So I'm going to keep working through the tutorials, and batches are going to be next, and then MPI, and I'll get all this working smoothly, and we'll do another session before too long.
Wait, can you do me a quick favor? Can you show your terminal for a second? I just want to see what you. So it was. Oh, so you went to the folder, and then Jupyter Notebook.
Yeah.
Or
yeah.
that's the-
Activate your environment
That's
first,
the
then you'll
file.
dive
It's
right
the
in it.
file. Okay. Yeah.
And then Jupyter Notebook will bring you in. And so if we hadn't activated our virtual environment, I guess it doesn't matter. Yeah, no, never mind. But it works if you got new. If you can do our virtual environment new, then it worked properly.
Mm-hmm. Yeah. Okay. That's fine.
And again, uninstall is just as easy as soon as we're done here, I'm going to delete this temporary directory. This has not affected my system in any way. And it's just a nice, clean way to run all this.
I have a quick question. How difficult would it be to change variables interactively and plot?
Very easy. Very easy.
Okay.
Let's see. Okay, so in the Jupyter Notebook, if you hit this double arrow to the right, click that, it'll restart and run all cells. So I'm just going to restart and run all those cells. And it'll take a little while, and it'll stop at this reset. So again, it's empty. So these cells haven't been run yet. Right now, what is it doing? Oh, here we go. So netparams dot. Oh, it crashed because I left netparams dot here, which crashed it. But no, so it's just cut this cell, run it all again. But so once this has all been run, then we should end up. Oh, here we go. Okay, so it stops at the reset, and I'm just going to say no. We'll just stay with what we've got. Nothing's done. All right, so let's do a new cell here, and let's do. Let's see what's in netparams. So I'm going to hit np tab dot tab, and let's modify that not add pop params, but let's look at the pop params. I'm going to hit tab now, and shift enter will show it. Great, so we see in pop params, num cells is 40. So let's do netparams.popparams num cells equals 80. Shift enter. Now we should have 80 cells instead of 40. Let's find that run command. Here we go. So I'm going to copy our run command and come back to the bottom here. Add a new cell and paste that run command into it, and then hit Shift Enter. Uh-oh. Some sort of problem. Int object does not support item assignment. Okay, so I did something wrong. Let's see what cells. What in the world? Okay, why does it keep jumping me forward? Anyways, I've messed around a little bit, but it's very easy to go in now and change any variable you want, and then you can just run this sim.create simulate analyze again, and it'll spit out exactly the simulation you've done, except with the change you've done.
Okay.
So yeah, it's very easy to do this interactively.
Thank you.
Yep. All right. Well, thank you all so much for following along. And so Craig, yeah, please post that issue, and I'll try to get this working on Linux as well. And people in the future, if you're watching this and you use Windows and you would like to see this on Windows, please let us know. If we have enough demand to do this on Windows, we'll get it going there as well. And yeah, thank you for your time, guys.
Thank you so much.
Thank
All
you.
right.
Thank
See
you.
ya.
That's great.
Okay, and I'm screen sharing more. Okay.